How can we, today what we are going to discuss is how can we have a Fourier representation for aperiodic signals, or I'm not saying finite duration signals, but aperiodic signals. Okay. For that, let us start with an example. This one we have already discussed. Like if you consider a rectangular pulse train, it is having fundamental period t naught, and let's say this is one interval of that rectangular pulse train, one period of that, and here it is non-zero from minus t1 to t1. And if you remember the Fourier series coefficients, this is a standard result. T naught ak is equal to 2 sine k omega naught t1 by, okay, let me write it as k omega naught t naught. Okay, you can also write it as k pi. K pi, yeah, it is, then this 2 will not be there. So anyway, we'll consider this form. Now, can you tell me what will happen if you increase the value of t naught? If you keep on increasing the value of t naught, what will happen to the Fourier series coefficients?
AK tends to 0.
AK tends to 0. Okay. And what will happen to the signal xt in the limiting case as t naught tends to infinity? As t naught tends to infinity?
0.
But 0. What is t
AK.
naught? Huh? Will it be this
AK
signal?
not 0.
Can
Yes,
we
sir.
say that this rectangular pulse, this is a periodic signal, and this is one period of that signal? So can we say that, can we represent this as a limiting case of this periodic signal? A periodic signal as a limiting case of that periodic signal?
Yes, sir.
As t naught tends to infinity, we will get this signal. Okay. And using this relation only, we are going to derive the Fourier representation for a periodic signal. That means we start with the periodic signal, find the Fourier series coefficients, and then we consider that a periodic signal as the limiting case of that periodic signal. Okay. So before discussing that, let us discuss this particular case. Okay, so this one. So you have seen that as t naught tends to infinity, the Fourier series coefficients are also tend to 0. Now let us consider ak into t naught. We can write it as 2 sine k omega naught t1 by k omega naught, isn't it? The reason why I am taking this is if we apply limit t naught tends to infinity, this also tends to 0. Now, if we consider a naught into t naught, that means we can say that these are the scale version of the Fourier series coefficients. AK are the Fourier series coefficients. We are multiplying that Fourier series coefficients with fundamental period t naught. Sorry, it is not A0, AK into t naught. Okay. Now, if we consider this one, can I write this as a function? Can we write like this? Sine omega t1. That means we are expressing it as a, let me denote it by x of omega, some function of omega. So this Fourier series, this scaled version of this Fourier series coefficients are, is it x of omega at k omega naught? Is it that? We are finding the scaled version of the Fourier series coefficients, and we consider a function of x of omega, that is in this case this one, and this scaled version of the Fourier series coefficients are, can we say that they are the samples? For example, if x omega is, let's say x omega is some function like this, what are these ak into t naught? What is the value when k is equal to 0? Is it this? And next value is when k is 1. because you want this Fourier series coefficients means ak from minus infinity to infinity. So this is the first Fourier series coefficient scale version, and next one is this is at omega naught, 2 omega naught, like that. So is this true? There is a function of omega and we are sampling at this instance. Is it that? This is a function of omega. Let's say this is a function and we are taking some values of that function. You will get these Fourier series coefficients. Is it?
Yes, sir.
Now let us consider this particular case. This is an interesting function you must have studied in your mathematics course. And in the mathematics course, you must have studied what is called a sinc function. Have you studied this function, sinc function?
No, sir.
No. Okay. Then let me define that function. Sinc, let us consider it as a function of time. Sinc t is defined as sine pi t divided by pi t. This is the sinc function. This is the definition of the sinc function. And this is a very important signal function in the study of signals and systems. Sinc function. This is called normalized sinc function. If you in some of the textbook, it is defined as sinc t is sine t by t. Okay, but this is we use this form of sinc function. This is called the normalized sinc function. We'll be using this form. Now, can you tell me what is the shape of the signal? Can you sketch this? This is a function of time. Can you tell me what is the shape of this function? Approximate shape.
So
Sinc t,
sine with magnitude decreasing
is it
towards
sine
as t
with
tends to infinity.
magnitude decreasing? Is it? Okay, tell me what is the value at 0?
0,
Is it 0?
Sir, 1.
It
1,
is,
1.
it is 1. And you are saying that it is sine with amplitude, decreasing amplitude, isn't it? Can you tell me where are the zero crossing points? Zero crossing points?
Sir, all integers.
All integers?
0.
All integers, it will be 0, because for any value of integer value of t, this term will be, numerator will be 0, isn't it? Is it?
Yes.
This is 1, 2. For all integer values, it will be 0. Is it an even function or odd function?
Even function.
It is an even function. Sine pi t by pi t is an even function. So the shape of that signal is something like this. Its amplitude decreases. This is the shape of the signal. Okay. At integer values of t, there would be 0 crossings. It is an even function of t. Okay. So this is the function. This is sinc t. Okay. This is sinc t. Now, what about this function? We are interested in this function. Okay, let me write it here. Ak into t naught, that is 2 sine omega t1 by omega at omega is equal to k omega naught. Now, can you tell me, is this some form of sinc function, this one? Can we convert, this is a function of what? What is the function variable here, independent variable?
Omega.
Independent variable is omega. So can we convert this into standard sinc form? What is sinc omega? If we consider it as a function of omega, then it is sine pi omega by pi omega. Is it? Here, this is sinc t. We are considering it as the independent variable is t. Now, if we consider it as a function of omega, then it is sine pi omega by pi omega. Now, can you convert? Can we express this in terms of sinc function? Tell me, what is this function? Can we write this as 2 sine pi into omega t1 by pi divided by is it that?
So T1 also in the denominator
By t1?
and numerator.
Oh, sorry, it is t1. Yeah, it is t1 omega t1 and t1, isn't it?
Yes, sir.
Now, what is tell me what is if we convert this into standard sinc form, can we write it as 2 t1 what? T1 sinc omega t1 by pi. Is it that?
Yes.
2 t1 sinc omega t1 by pi, where sinc omega, this one is this one. Okay. Okay, now let me write it here. So we have Fourier series coefficients. And this ak into t naught, what we got is 2 t1 sinc omega t1 omega, I think it is omega t1 by pi, isn't it? So omega t1 by pi. This is what we have proved. Okay. Now let us, so we can say that this is a function of omega. For the scaled version of this Fourier series coefficients, we can get from this function by sampling it at this instance when omega is equal to k omega naught. Okay. Now, can you tell me what is the shape of this function? Is it this is a sinc function, isn't it? Sinc function means this is the shape. Its amplitude is decreasing. Tell me where are the zero? What is first? Tell me what is the value here?
2T1.
It is 2t1. And this point, where are the zero crossing points?
Pi by T1 times integers.
It is pi integer multiples of pi by t1. That means this is pi by t1. This is 2 pi by t1. This is minus pi by t1 minus 2 pi by t1, like that. It is integer multiples of t1, isn't it? Is it? Okay. So these are, if you remember, we are starting with the Fourier series rectangular pulse train, and its fundamental period is t naught. We'll get Fourier series coefficients ak. Now we computed the Fourier series, the scaled version of the Fourier series coefficients, because we are taking this scaled version, because if we don't multiply with t naught as t naught tends to infinity, this Fourier series coefficients will tend to 0. Now we consider this, we got that, this one. Now let us consider few special cases of this. First, let us assume that T1 is equal to, T naught is equal to 8 T1. Okay, these are the cases, these examples are given in Oppenheim, that is why I'm explaining the same thing. If we consider T naught as 8 T1, Okay. Now what is omega naught? This point is pi by t1, right? Zero crossing points are integer multiples of pi by t1. What is omega naught? 2 pi by t naught. Can we write it in terms of t1? Is it pi by what? In terms of t1? Is it this? I am considering a special case. T naught is 8 times t1. So then omega naught is pi by 4t1. Now we have to sample, this is this function. We have to this sample at the values of k omega naught. K t naught. What is the first value of this A0 into t naught? Is it this? Let me choose a different color. So is this value? When k is 0, A0 into t naught? Is it that?
Yes, sir. Yes.
You are putting this value here. When you want to find A0 into t naught, put this 0. So it is this function at omega. This is a function of omega at omega 0. And where is the value? Where is this point? A1 into t naught? First Fourier series coefficient multiplied with the Fourier this one. Where is that point? Put k equals to 1. So it is at this point. Where is that point? What is omega naught in this particular case? Is it, what is that? Pi by 4 t1. This is pi by t1. So, okay, I have started with the wrong value. Okay, let us start with let's say t naught is 4 times t1. In that case, omega naught is 2 pi by t naught. This is 2 pi by 4. So this is pi by, so here in this case, omega naught is equal to pi by 2t1. So is that point here? This is the next value, this one. Then you will get this value, this. Is it that? You sample it. This is 0, omega naught. Here omega naught is pi by 2t. This is pi by t1. Pi by 2t1. So this is the point. This is like that. Okay. So can we say that the scaled version of the the Fourier series coefficient we can get by sampling this function? Is it that?
Yes, sir.
Now what will happen if we increase the value of t naught? If we increase the value of t naught, let us consider this. T naught is 8t1. What is value of omega naught in that case? Is it pi by 4t1? This one is pi by 2t1. So if you calculate that, these are the points. Okay, first point is this one, this will come, then this. It is like this. The samples will increase because this distance is omega naught. If we increase the value of t naught, what will happen to omega naught? This is omega naught. If we increase the value of t naught, what will happen to omega naught?
Decreases.
It decreases. And what will happen in the limiting case? As t naught tends to infinity, what will happen to omega naught? Omega naught tends to
0.
tends to 0. Then what will happen to this function ak into t naught? Can we say that it approaches this envelope function in the limiting case? Is it that? Because if we decrease the value of omega naught, this spacing will decrease, isn't it? And in the limiting case, as omega naught tends to 0, it approaches this this function. Okay. And in the limiting case, what will happen to this xt? It approaches which function? Which function? What will happen as t naught tends to infinity? Will it approach this function? Is this the function, the limiting case of this? This is xt, limit t tends to infinity xt. Is it this? Only one pulse. Okay, so that is how we, and this is called, I'll define it, the actual definition I will explain shortly afterwards. But here you can see that corresponding to a rectangular pulse, because the limiting case of this is this rectangular pulse, corresponding to that there is a function in the frequency domain. Okay, that is this envelope function. Okay, and this is called the Fourier transform of xt. This function is called the Fourier transform of xt. Consider a function xt. It is an aperiodic signal. Let's say this is the signal. I am taking it as minus t1. It is not a, it is an arbitrary shaped signal, but it is a finite duration signal. And I am considering it as from minus t1 to t1. It is non-zero only in that interval. That is a function xt. And whatever I have taken this symmetry to simplify the analysis only, even if it is not symmetric or like different duration, the whatever we are going to derive, that will hold for that also, that cases also, because I have considered this minus t1 to t1 because the derivation is easy in this case. Okay. Now, first we have to make it a periodic signal. We have to consider it as a limiting case of a periodic signal. Now, if I consider this signal, okay, let's say the shape is like this. This is 0 t1 minus t1. This is the same as this. Then this one shifted by t naught, like that. We are making a periodic signal from this signal, from this aperiodic signal, and I am denoting it as x tilde t. Now, can you tell me what is the mathematical expression for this x tilde t? What is the mathematical expression?
So summation from k equal to minus infinity to infinity.
Okay, I am writing it as summation from m, because k we are using for Fourier series coefficients. From minus infinity to infinity, what?
So x t plus
Xt
m
plus
time
or minus mt naught, isn't it? Is it? That is a periodic extension. We can say that it is a periodic extension of this aperiodic signal. Since this is a periodic signal, we can have a Fourier series representation with respect to period t naught. Let me denote it by ak. Okay, now what is the expression for this ak? That is called the Fourier series analysis equation. If you are given a periodic signal, we can find its Fourier series coefficients using the Fourier series analysis equation. Is it this? Integration over t naught. X tilde t is the periodic signal. You have to multiply it with e raised to minus j k omega naught t dt. That is the Fourier series analysis equation. Remember, this is period. This is integration over one period, and this is the periodic signal. Can I write it as 1 upon t naught integral minus t naught by 2 to t naught by 2. I am considering interval here. This is, let's say this is t naught by 2 and this is minus t naught by 2. In this interval, x tilde t e to the power minus j k omega naught t dt. Okay. Now, can I write this as 1 upon t naught integral minus infinity to infinity xt raised to minus j k omega naught t. Look, here it is
Yes, sir.
x tilde t, and this is xt, because xt is 0 outside this interval. So we can replace this with xt, and limit we can change from minus infinity to infinity, isn't it? Because it is our 0 outside this interval. We are integrating over this interval x tilde t, that is same as integrating xt. Is it?
Yes, sir.
Now what is this ak? This is ak, isn't it? Now what is our objective? Our objective is that as t naught tends to infinity, this Fourier series coefficients multiplied with this t naught that approaches some envelope function. In the case of for a rectangular pulse train, it was a sinc function. Now what we are trying to do is we are trying to find a general expression for that envelope function. For a rectangular pulse, the envelope function is a sinc function. Now, if you are given an arbitrary shape xt, what is the shape of that envelope function? That is what we are trying to find here. So here, that envelope function is ak into t naught. That is integral minus infinity to infinity xt e to the power minus j k omega naught t dt. Isn't it? Now, can we write this as integral minus infinity to infinity xt e to the power minus j omega t dt at omega is equal to k omega naught? Is
Yes.
it that? Yes. Now, what is this function? Is it the envelope function? What is the meaning of this? ak into t naught, that is Fourier series coefficients multiplied by this the fundamental period of that signal, that is that we can get by sampling this function at k omega naught. Is it that? Okay, so let me denote this by xt into e to the power j. I'm defining a function capital X omega, function of omega, that is defined as integral minus infinity to infinity xt into e to the power minus j omega t dt. What is this? This is called the
Fourier transform.
This is called the Fourier transform of the signal xt. You must have studied have you studied this form of Fourier transform or some other form? You have studied it in your mathematics course, isn't it?
Yes, sir.
This is called the Fourier transform of xt. Given a signal, a periodic signal xt, its Fourier transform is defined as this integral, that is denoted by x of omega. Okay, x of omega. If we have a signal xt, its Fourier transform, it is defined as integral minus infinity to infinity xt e to the power minus j omega t dt. Okay, and this is the form of Fourier transform that you have already studied, but we'll use a slightly different version of this. Different version means I denote it by x of j omega, not by x of omega. It is x of j omega. I am following the notation used in Oppenheim. It is denoted by x of j omega. This is the Fourier transform that is defined as integral minus infinity to infinity xt e to the power minus j omega t dt. It is instead of x of omega, I am writing it as function of j omega. And there is a reason for that. Can anyone tell me what is the reason for this? Why am I writing x of j omega? I'll give you a hint. What is the Laplace transform of a signal? What? Laplace transform also you have studied in your maths course. What is the Laplace transform?
R minus st dt integral.
Is it this?
Yes.
Yes. So there is a relation. What is this S here? It is a complex variable, and sigma is the real part of that, and we can take omega as the imaginary part of that. The reason why we are using this is to study the relation between Laplace transform and Fourier transform. You can easily see from here what is the relation between the Laplace transform and Fourier transform. Can we write that x of j omega is x of s? Is it that? When the real part of this complex variable s is 0, we will get the Fourier transform. So there is a relation between Fourier transform and Laplace transform. We'll discuss that later. Because of that reason, in order to find that relation, we are using it as a function of x of means we write it as x of j omega instead of x of omega. Okay, then we can directly replace these variables. That is the reason why we are using x of j omega. Okay, so this is the definition. If we have a signal xt, its Fourier transform, it is defined as x, so it is denoted by x of j omega. This is the definition. Okay. Now let us see, are we getting the, whether we are getting the same result or not. 0 t1. Okay, we are considering a signal that is of duration minus t1 to t1. This is a signal xt. It is an aperiodic signal xt. What is the Fourier transform of this signal? This is the definition. So you get x of j omega as this one, integral minus infinity to infinity, this one. So can we write it as minus t1 to t1, because the function xt here is non-zero from minus t1 to t1 only, into e to the power minus j omega t dt. Will you get the same result? You can verify it. Earlier we got the Fourier transform of this as 2, I think it is 2 t1 sinc omega t1 by pi. You should get the same result if you integrate this.